Okay, we do have one more, the RF ingress noise and distortion section. I know we're over time, but do you want to keep motoring on and try and blast through this pretty quickly, Larry?
Let's do this and we'll get it at least recorded. And if people want to come back and check, otherwise we can schedule another. But let's do it and get it recorded, Mike, so that you can use it for your show.
Awesome. All right. RF ingress noise and distortions. So if you were to take a good antenna and a spectrum analyzer and just survey the air and see how much actual electromagnetic energy is bouncing around our environment, it might make you want to crawl into a cave and put on a tinfoil hat. There is a lot of energy bouncing around over the air. Now, cable, by definition, is a closed system. And we haven't talked much today about shielding integrity or shielding effectiveness, but the cable systems, being defined as closed systems, have been built so that the shielding can withstand any of that energy that is bouncing around over the air from intruding into our cable systems, which we do leakage as a test and proof that we're measuring the shielding effectiveness of our cable systems. Now, there are instances, and very often, points in the system, whether it be in the hard cables or in the drop systems, where the shielding itself is impacted. And when the shielding is impaired or defective, then it can allow anything over the air to ingress into the system. Now, there is a semantic difference between ingress and noise, but we're not going to pick that particular fight today. But suffice it to say that ingress and noise can be very difficult to keep out of our system. But if we understand our environment and what over-the-air signals are out there based on your particular geography, if you're in a major metropolitan area with a large population, it's likely that you may have more over-the-air signals to support that population, whether they be over-the-air VHF high-definition television channels or FM radio channels or cellular signals. There's a tremendous amount of energy out there which can affect different portions of our spectrum if the shielding is affected. In this first example, we see lots of impairments, but we want to draw particular attention to this first peak here, which, if you'll notice, is in the 87 to 108 megahertz range, which is occupied by FM radios. So we're detecting at a very high level FM radio stations that are being interpreted by the customer premise equipment as energy in the downstream. So once that energy defeats the shielding of our cable and is introduced into the center conductor of the cable doesn't care what the signal type is. It's going to move those electrons, all the way to termination. And in this case, the termination is the set-top box. So somewhere upstream of this device, there is a shielding integrity defect that allowed the FM radio signals to gain access to the cable, be coupled to the center conductor, and transmitted all the way to this device. Now, there are other over-the-air signals that are in this as well, but the FM is the most egregious in this particular instance. All of these devices show some incidence of high FM ingress in that 108 megahertz region. Now, you'll also see other signal types, typically around 860 megahertz. That's would be a T-Mobile LTE signal. We may see them in the 500, 600, 700 range, megahertz range as well. But other over-the-air signals also exist depending on your market and can be visualized on the downstream full band capture of these devices. Anything that I left out, Larry?
No, well said, Mike. But wait, there's more.
But wait, there's more. So
yeah, this is a great visualization. Basically, this is a superposition of our cable signals and everything else that's off air. As Mike earlier alluded about the aluminum foil in the cave, aluminum foil hat, there's a lot of stuff floating around in the air. And this is pretty obvious that the effectiveness of our shielding is not working well, and in fact our system appears to be a very good antenna for the entire frequency spectrum, because the off air is actually louder than our stuff that's supposed to be there. And this is going to be typical of what you would expect to see if you go see. There's a recent example of there's a cable coming off out of the side of a house, and the dog had chewed and stripped all of the shielding off, and there's about a 6-inch center conductor with no shielding whatsoever. This is exactly what that frequency spectrum would look like in that case. So unfortunately, more common than you would hope to or expect to see.
But it's out there. So to that end, these over-the-air signals in some more modern deployments like mid-split can actually show up in the upstream as well. So this is two different devices inside of the same home, or the spectrum analysis plot on the upstream on the lower right is a CMTS burst receiver capture of a particular node. And you can see that there are two channels that are very persistent and prominent in the return path of this node. Now, if you were to look at a video set-top box in this same node and do a downstream capture, you'll see those same two channels. This is a VHF over-the-air channel 2, right, and channel 6. But depending on the device that you look at, on a subsplit diplex device, that signal is interpreted as downstream signal. But in a mid-split device, that signal is interpreted as upstream signal. While it's the same source, it's impacting very different services based on the device in question. So this one also has very persistent and high-level RF or FM radio noise, but you can see VHF channel 2 and channel 6 on some devices interpreted as downstream, and other devices interpreted as upstream.
Tricky. That's why I put the slide in there, Mike. Remember, what you're looking at, the graph down on the lower right-hand corner is the head-end view. That's from the burst receiver. And then the graph on the left side is the cable modem view. So you're looking at the exact same impairment from different places on the network. One device considers it upstream, the other end considers it downstream. And this is going to get really tricky as we start to go full duplex, for example, where upstream and downstream become one and the same. And so we're going to have to pay a lot of attention to things like, ingress and egress at different places in the frequency spectrum, because now they're going to affect everybody, not just that one customer, when we change directions.
So while the symptoms are different, right, we're looking at from the upstream and the downstream perspective, the cause is the same. We have an over-the-air signal source and a shielding defect in the cable that allows those over-the-air signals to be coupled into our center conductor. And so in this particular scenario, if we were to find that shielding defect in the cable network, we could solve an upstream and a downstream problem with the same repair. So at the end of the day, we want to connect the symptoms that we use our intelligence tools to detect with the causes of the actual impairment itself. So a singular cause could have actually multiple symptoms in either the upstream or the downstream, depending on the condition and the type of impairment in the cable. Let's talk about distortions. So this particular view, again, a burst receiver capture at the CMTS, and this particular distortion is common path distortion. So this is a reflection of downstream energy back into the upstream. It's typically caused by corrosion that affects two different metal types. So there's a lot of connections in the cable plant, right? From your copper clad aluminum center conductor that goes into maybe a nickel plated pin connector, which then is connected to a tap seizure mechanism that may be different metals than the pin on the hardline connector. Lots of dissimilar metal junctions in the cable network organically. Now, when they're all properly installed and clean, everything works fine if we have matched nominal 75 ohm impedance. But sometimes we get corrosion into the system, which is typically a shielding defect that lets water in, and it corrodes those metals. So when those dissimilar metals become corroded, it creates a diode that, think about it like a mirror that's partially see-through, but will reflect some of the energy back in the way that it came. So the downstream signals are reflected back into the return. Now, in olden days, when some of us started, we had analog signals in our downstream channel plan, where you had your video carrier, your color burst, and your audio carrier that were 3 different peaks or signatures in RF. And when those were reflected back, we had these evenly spaced 6 megahertz spikes in the return path, because the channels on the downstream had the video carriers that were fairly precisely 6 megahertz apart, with some minor variations. But in the digital networks today, where all of our downstream channels are digital and they're relatively flat haystacks, we see this common path distortion look like elevation. So that is actually the reflection of digital downstream channels into the return path. Now, you'll also notice this shoulder at the edge up here around 42 megahertz. That is the effect of the diplex filter in the active devices, meaning the amplifiers, or potentially the node. So that energy in the downstream is being reflected back into the return, and the diplex filters in the amplifiers is causing this roll off or shoulder. So that type of distortion is common path distortion.
Yeah, I'll go back one quick note on the shoulder there. If you see that and there is no shoulder, then it's probably not a source of coming through the RF path, right? Because you would normally see the rejection of that filter there in the shape of the shoulder. Then you probably have a laser issue or other types of things. So that's just a really quick sanity check. Laser or distortion. If you have a high noise floor, there's a couple of different things. Check for that shoulder roll off there. To see if it's coming through the filters on the RF plant or if it's probably optically related.
Good point, Larry, because we have seen laser clipping that sometimes can look like CPD. However, in the laser clipping scenario, you won't see that diplex filter roll off because it's happening between the optical transmitter and the node and the receiver and the head end. Okay, HPNA and GHN. I know this is something that you've been pretty passionate about and watching closely.
Sorry, Mike, your audio dropped out for a second.
Oh, I said HPNA and G.HN is something that you've been watching closely lately.
Yes.
Do you want to tell us what that is?
You bet. So both are actually, it used to be called HPNA, which is Home Power Network Adapter. I think there's a couple of variations it's changed. And then G.HN is a new standard that has surpassed HPNA has been absorbed into G.HN. It's basically an OFDM signal that's used by competing technologies that ends up on our coaxial network when it's not supposed to be. So for example, think about the way that MoCA works. In-home signaling from box to box on UVerse, for example, uses HPNA and certain FiOS and a couple of others, where they will basically take the existing coaxial in our houses, connect the boxes, hey, it's conveniently there already, and they'll transmit from set-top box to gateway using our coaxial cable in our upstream frequencies, which is in theory fine, except for if you leave it connected to our plant, you basically now have an OFDM signal generated that's interfering with our return frequency spectrum, and so that's exactly what it looks like. What's the frequency width or the spectrum width of that the typical HPNA, Mike? Remind me.
So typically, HPNA only extends out to about 30 megahertz or so, and any carriers above about 34 or 35 would not be impacted by the traditional HPNA signaling from those fiber-based providers.
Yeah, and about 20 megahertz wide, maybe, is that right?
Yes.
Yes.
However, G.hn is a different story.
Yeah, so now all of a sudden, hey, look how convenient this is, and all this extra spectrum we can use, and you're starting to see it above 100 megahertz, which affects our mid-split, high-split, full duplex, and all these other things. And typically, because it's because of our forward coupling, that would affect the downstream of that house, and they're not a customer, so they don't feel it. But when we go into a mid-split and full duplex in these high-split environments, it starts to become an upstream problem where the entire node now gets wiped out because one customer switched to a competitive product and left connected to our plant. One really handy trick for troubleshooting these is if you have a node that's suffering from HPNA or soon to be G.hn, look and find the recent disconnects. And these are customers who've left their plant connected to Comcast, had, maybe a self-install kit or a poorly done pro install of, AT&T Uverse while they're still connected to our plant. And that's a really super helpful technique.
Yeah. So irony of ironies, at the beginning of the broadcast, we talked about the differences between DOCSIS over coax versus the fiber-based providers. But the irony here is that fiber-based providers actually use RF over coax inside the home. So when we're not properly isolated from those fiber-based providers that are using coax and RF to communicate inside their premises, that can actually make its way back onto the coax network from the DOCSIS providers.
Well, they're just being opportunist, right, Mike? There's a perfectly good coax sitting there between rooms. Why not use it?
That's right. Okay, so that is the end of our show, and I apologize we went a little bit over, but we had a lot of material that we're really excited about, and we wanted to share with you. So Larry, as always, it's been a huge pleasure. Appreciate you and all of the work that you do, both inside of Comcast and for SET and Cable Labs, and your leadership on the working groups in the subcommittee.
Yeah, so, likewise, Mike. Appreciate you too, and Penn, and looking forward to getting out there and spending a little time with you this summer.
Yep, agreed. So this photo was taken a long time ago at SET Expo with the Honorable Mr. Ron Hranek and us. So that was a great collaboration that continues on through today, and the output of papers like OP280 and a little teaser. We're working on the upstream companion document in Working Group 7, which will be published as soon as it's ready. So more good stuff to come.
Great. Okay, thanks. I'm signing off. We're way over. Thanks for hanging in there, gang. Appreciate it.
Thanks. I'll appreciate the comments. As always, if you're not a member of SET, please consider joining. It may be a company benefit if you look into it, and affiliate with a chapter in your local area and experience the whole benefit of SET and its chapter structure. So with that, thank you all. Have a great day. Larry, as always, it's a pleasure.
Cheers.
Signing off.
Bye-bye.